Hello everyone. Today we are going to look at the idea of Fourier transform. Okay, if you watch my previous video, I have explained to you about Fourier integral. Okay, so this is Fourier integral looks like. The definition of Fourier integral is given on this interval here. Okay, f of x equals from 0 to infinity a omega cos omega x plus b omega sine omega x differentiate respect to d omega. Okay, where a omega is given by 1 over pi integrate from minus infinity to infinity fx cos omega x dx, and b omega is given by 1 over pi from minus infinity to infinity fx sine omega x dx. Okay, so this is the definition of Fourier integral. Now, to do Fourier transform, we want to show the transition from Fourier integral to Fourier transform. Okay, so we want to express this now, this equation, let me call this equation 1 now, in a complex exponential form. Okay, so what we're going to do here, okay, we want to first put the Fourier integral coefficient here, a omega and b omega, into this equation. Okay, we want to include this, we want to put this into this equation, these two a omega and b omega given. Okay, let's do that. So we have fx equals to, okay, so 1 over pi, we have two integral, one is this one, 0 to infinity, and then this integral, minus infinity to infinity. Okay, and then we have a omega, okay, so we have cos omega x, okay, so, and then we're going to use b omega given by this one. Okay, so remember that to do that, we cannot just simply substitute this inside this equation. Okay, we need to be careful when we're doing that. We need to change the dummy integral here. Okay, the dummy integration, variable x, this variable x here, okay, you want to change it to change x. My x is not, okay, change x to, let's say, xi. Okay, change x to xi, because we don't want to have we don't want to get confusion with the variable x in this equation here. Okay, so to do that, let's write it now. So my AW is a of omega, which is a omega here, which is f xi. It will be f xi. Okay, and then we have cos omega xi. Okay, this is for this part over here, and then don't forget my cos omega x over here. Okay, I hope you are with me. And then we have plus my b omega term now. Okay, where b omega is here, but my x will become xi and this will become xi, right? So I have f of xi sine omega xi sine omega x. Okay, now we have term, we have variable involving d omega and d psi. Okay, d psi, d omega. Okay, maybe I can factor out my f omega. And then if you look at this cos, sine, right? Cos, sine, So I can write it as 1 over pi 0 to infinity minus infinity to infinity f of xi cos omega xi minus x. These are the property. Okay, the property of trigonometry. Okay, so let's put a bracket here. Okay, so this is how we can simplify to this equation. Let me just call it equation number 2. So just recall what we have done so far. So the idea of Fourier transform, to get the Fourier transform equation, what we got to do is we got to use the Fourier integral definition. This is the Fourier integral definition, and I want to first start by substituting my a omega and b omega into equation 1 here. Okay, but bear in mind that when you do that, you need to be careful with this x in a omega and the x in this equation 1. So I need to change my x to xi so that I will not have the confusion of the variable, these two variables here. Okay, so by doing that, if you see x in a omega and b omega, that will become my xi. Okay, and then put that into this equation. So this is what I get, f xi cos omega xi. This is actually my a omega. Okay, this is from the equation itself. And this term here is my b omega. Okay, now by using the trigonometry identity formula, cos, sine, and factoring out my f omega, I should get a simplified version like this. Okay, maybe I will write a note here where cos a minus b is equals to cos a cos b plus sine a sine b. Okay, now next step is what we want to do. We want to express this cos omega xi minus x in terms of complex exponential form. Okay, so if you don't have any idea of complex exponential, okay, maybe I can give some of the basic formula for complex exponential of cos and sine. Okay, to do that, you can actually Google it. I mean, if you're not idea, but you can just Google it. So the complex exponential form for cos, okay, maybe I'll write a note here. So we have cos u equals to e iu plus e negative iu over 2, and then sine u equals to e iu minus e negative iu over 2i. Okay, these are the complex exponential form for cos and sine. Okay, so now what we want to do, we want to write this form here, this cos omega psi minus x in this term to the form of complex exponential form. Okay, let's do that. Okay, so looking back to equation 2, So from equation 2 here, what we have, fx equals to 1 over pi integration from 0 to infinity, and this is a double integral, negative infinity to infinity, f psi. Now my cos here will become eiu, where my u is the whole this term here, okay? So bear with me, I have omega psi minus x, that's for my u here, okay? And then plus negative I, and u again, omega psi minus x. Okay, so don't forget divide by 2 here. Okay, this is the exponential form. Okay, and don't forget I am integrating respect to d psi and d omega. Okay, I think I can simplify this integral here. Okay, take the 2 out. Okay, so 1 over 2 pi integral from 0 to infinity, from negative infinity to infinity. Okay, we wanna I think we can split this interval. Okay, so we have 1 with f psi I omega psi minus x. Okay, I can actually take the omega out, but that's okay. So d psi d omega plus 1 over 2 pi integrate from 0 to infinity minus infinity to infinity. Now the other term for f psi. Okay, so I have f psi negative I omega. Now this term now, I omega psi minus x. Okay, so we have from d psi d omega. Okay, so this is gonna be a bit tricky. Okay, there are terms that we can combine. Okay, the terms that we can combine. To combine the next 2 terms here on the right hand side, we want to change the dummy. Okay, we want to change the dummy from omega to negative omega. Okay, so we want to, okay, let me just write it down. Change the dummy integration variable from omega to negative omega. Okay, so when we are changing the variable from w to negative w for this part here, for this part, okay, so this integral will change the sign. Okay, so now we will have fx equals to 1 over 2 pi 0 to negative infinity, infinity. So we have negative infinity because we want to change this this omega here and this omega to negative omega. So we have f psi I negative, okay, negative I omega, become negative, psi minus x, and then d psi negative d omega. Okay, that's why this integral we have negative infinity. The rest will remain the same. Okay, from 0 to infinity, because we are not changing on the right side of the integral. Okay, so this will remain the same. Now the purpose for doing this, so we can have the same integral here. Okay, that's the purpose. Now this is not quite same yet, but I can combine. If you look at this negative here, now with this integral, I can take it out and the sign will change. Okay, so we have 1 over 2 pi. Now we will have negative infinity to 0. Okay, from negative infinity to infinity, f xi e negative I omega xi minus x d xi d omega. Okay, the negative disappear because I swapped the integral. And then 1 over 2 pi, we have 0 to infinity, the rest remain the same. Okay, now I get to see what's happening here. I hope so. Okay, so now we can combine. Okay, this is from d xi d omega. Okay, now we can combine these two integral. Okay, so now we have 1 over 2 pi from negative infinity to infinity. And then we have this double integral f of xi, factoring out this term, right? So we have e. Okay, so e negative I omega xi minus x d xi d omega. Okay, so this is the simplification for the transformation we can make. Okay, they are not quite yet finished, but for simplicity, I am going to write this like this equation now. Okay, so I have I'm going to put a bracket here so that you can see what's happening. E negative I omega psi minus x. And then what happened? So this is d of psi, d of omega. So I think I want to take out the psi and omega, okay, to outside this bracket. So I can have integrate from negative infinity to infinity f of xi e negative I omega psi d xi, and then e I omega x. So you just expand this term here. Okay, so that'll be positive d omega. There you go. So this equation 3 that you have obtained can be divided into two equations. Okay, so I can write this as capital F inverse f hat omega equals to fx. Okay, so what is the fx here? It will be 1 over 2 pi from minus infinity to infinity half hat omega e I omega x d omega, where for omega from negative infinity to infinity. Now look at what happened here. Okay, this part here becomes half hat omega. Okay, so this is called the inverse. This is the inverse Fourier transform. Okay, where we denoted by F inverse. Okay, and what is half hat omega? So maybe I need to write it down, where f, the big F, let me just adjust this, where the big F, keep making mistake. Okay, the big F, I want to write it like this. Okay, the big F, F omega, okay, equals to f at omega, which is the inside integral from minus infinity to infinity, f x, okay, f x e negative I omega x dx for x from negative infinity to infinity. Now this is the Fourier transform. Okay, remember earlier on I've to avoid the confusion, I have written my x as xi. Okay, so what I did now, I change it back. Okay, so this part here, if you look at here, change x to xi. So my x all becomes xi, right? So the reason I'm doing that, so that you won't get confused at the end. But when you are writing back the Fourier integral, you have to change it back to x. Okay, my your xi is become your x. Okay, so what is this? This is the definition. The definition of Fourier transform. Okay, Fourier transform is denoted with this notation. Big F, f of omega. Okay, and the inverse Fourier transform is given by f inverse, half of hat omega. Okay, in certain book, they use different notation where you have 1 over square root 2 pi. Okay, but there is another way to transform that, but I'm not gonna show you in my video because we're gonna use this definition towards the end of the lesson. Okay, so we have two definition. Okay, given by, we have two definition now. I'm just gonna write it back. Okay, one is the Fourier transform given by f hat omega. Okay, from minus infinity to infinity, f x e negative I omega x dx. And then the other one is inverse of this, inverse of half at omega, which is given by 1 over 2 pi from minus infinity to infinity, half at omega e I omega x d omega. Okay, remember the f hat omega here is the complex equivalent of a omega and b omega from the Fourier integral. Okay, so this Fourier transform exists under the same condition as the Fourier integral, but it is defined on this interval x from minus infinity to negative infinity to infinity. Okay, so if you understand this, maybe I can look at one simple example on how to use this formula. Okay, let's look at this example here. Okay, the example is given as find the Fourier transform. In certain book, they use the word ft for Fourier transform for the given function. Okay, so fx equals from piecewise function from 0, 1 and 0 if the absolute x is less than a, and then 0 if this x, absolute x, is greater than a. Okay, so find the Fourier transform. Let's find the Fourier transform. Okay, I'm going to use a different marker for that. Okay, so use the definition of Fourier transform. Such that, what's the definition of Fourier transform? This one. Half at omega equals to this equation here, pretty much this above equation, from minus infinity to infinity, fx e negative I omega x dx. Okay, now we gotta look in, this is the definition. Now we gotta substitute my fx using this two piecewise function. Okay, so it is, so if you look at this integral, it's less than a 1 and greater than a is 0. So we have the integral from minus a to a. Okay, let's consider for 1 first. Okay, this 1 because 0 is, you don't have to integrate that. So 1, fx is 1, e negative I omega x dx. Okay, so we have to integrate that equation. Okay, I don't see any difficulties in integrating this. Okay, so that'll give me e negative I omega x, integrating x, differentiating x will give me negative I omega. This is from minus a to a. Okay, taking out the constant for now, which is I omega, I have e negative I omega a minus e negative I omega negative a. Okay, now simplifying this equation, I have negative 1 over I omega. So this term will give me a positive sign. Okay, so I have e negative I omega a negative e I omega a. Now if I wanna take this negative inside, that will give me 1 over I omega. Negative will be e I omega a minus e negative I omega a. Okay, so earlier on I've given you the definition of the complex form of sine. Okay, I've written somewhere up here. Let's see if we can find that definition. I think it's the beginning. Okay, when we wanna change this in the Fourier integral to Fourier transform, I've written some of this definition. There you go. There you go. This one. Okay, so this is what looks like. Okay, sine u. So we have sine a omega. Okay, if u equals to a omega, so we have sine a omega equals to e I a omega minus e negative I a omega over 2i. Now we are gonna use that to our computation below. Okay, we're gonna substitute that. Okay, so maybe I'll just write it here. Sine a omega will give me, so I'll just write it properly. Okay, this is the note so that you know, or easy to remember in the future. So the note is sine a omega equals to e. Okay, e I a omega minus. Okay, is it minus or plus? Okay, so if it's sine, it is minus, but if it's a cos, it will be plus. Okay, so e negative I a omega over 2i. Okay, so we want to change this, but we need to have 2i sine A omega equals to E I A omega minus E negative I A omega. See, A omega or omega A, there shouldn't be any difference. Okay, so we have 2I sine A omega. Okay, so looks like we have come to the conclusion for the Fourier transform. Okay, the Fourier transform for that piecewise function, I can cancel out my W, my I, that'll give me 2 sine A omega over omega. Okay, so that's the solution for this question. Very simple piecewise solution. Now, if the question said something like, okay, something like find the inverse. Okay, maybe I can show that too. Okay, if this is the first this is the part A here. Part A here where you find the Fourier transform, and the next part now something like this. Express F as an inverse Fourier transform. Okay, how we want to express this as an inverse Fourier transform. Okay, to do that, recall the inverse Fourier transform definition that we had looked into just now. So the inverse of Fourier transform is given by fx equals to 1 over 2 pi, integrate from minus infinity to infinity f hat omega ei omega x d omega. Okay, look at the difference between the Fourier transform and the inverse. Okay, the Fourier transform, you integrate with respect to dx, and then there's the negative sign here. Okay, but the inverse Fourier transform, you are integrating with respect to d omega, and there is no negative here. And also this one will now refer to this Fourier transform that we have solved earlier on. So change it back from minus infinity to infinity. 2 sine A omega over omega ei omega x d omega. Now this is gonna be a bit difficult, okay, because we are integrating with respect to d omega. So how can we simplify this? I think we have to use some of these complex form of sine and cosine again. Complex form of sine A omega. No, not complex form of sine A omega. Complex form of ei omega x. Okay, so if sine can change to exponential form, now exponential imaginary can also be transformed to cos and sine. Okay, so you need to recall the definition of the complex exponential, where ei theta equals to cos theta plus I sine theta. Now this is what we are gonna change for this part over here. Okay, so let's do that. Now my 2 and 2 can cancel out. That's give me 1 over pi from negative infinity to infinity. Okay, exponent I omega, I'm gonna change that first. That will give me cos. Okay, what is my theta? Theta is omega x. Okay, so we will have cos omega x plus I sine omega x. Okay, cos omega x plus I sine omega x. And then don't forget my sine a omega over omega. Sine a omega over omega. Okay, I'm just gonna erase this. D omega. Okay. Okay, now let's see how we can simplify this. So I can pretty much multiply the sign inside the okay, so that will give me maybe take out 1 over omega cos omega x sine a omega. Would that be positive or negative? Okay, this will be positive plus I sine omega, a omega or sine omega x sine a omega d omega. Okay, continuing what we have here. So if you look at this term here, sine omega x sine a omega. Okay, so this is an this term here is an odd function. Okay, odd function. So the integral is 0. Okay, the integral here will be 0. That will leave us with 1 over pi from minus infinity to infinity cos omega x sine a omega over omega d omega. Okay, so this is the best solution that you can leave it to. Okay, you don't have to integrate, you just leave because the question said express. Okay, express f as an inverse Fourier transform. So we're going to leave our solution like this. Okay, so I hope in my next video you can see some examples of Fourier and inverse Fourier transform. Okay, but yeah, I think that's all for today. The introduction to Fourier transform, the derivation of Fourier transform, and one simple example of Fourier transform. Okay, keep watching my next video for more examples on solving using Fourier transform. Bye for now. See you next time.